So what we're doing is composing all these. Really, if we think about it, I'm going to define, let's say the pink ones, the activation functions is G, and we'll just use the blue ones as F. So we are computing, y hat equals G, this last G, sub L of F sub L of G sub L minus 1 of F sub L minus 1 of eventually of G sub 1 of F sub 1 of X. That is a neural network right there. You define, well, and we know what our F's look like. Our F's, all of them are going to look like, right? F sub I equals F sub I of our, whatever our input is, equals X WI plus BI. And so we define what each G is, right? Which kind of a nonlinear function it's going to be. We define the sizes of each of the layers, and that is our function, right, in our entire neural network model. And then all we got to do is train it, which we'll have to learn how to do. Let's rewrite this a little bit. Okay, so let's just go through linear as we actually calculate it. So we're actually going to go through from the beginning to the end. So we're going to go ahead and define Z is going to be the output of F. So Z sub 1 is going to equal X, our actual input X, times W1 plus B1. And W1 is of what size? Well, it's going to be the number of inputs times however big we want to make it. So we call that S1. And B1 similarly is going to be 1 times S1. And then we'll say that A is the output of the activation function. And A because it's an activation function. So we're going to go ahead and say A sub 1 is going to be equal to G1 of Z1. Right? So now A1 has the same form as B1 does, in the sense that A1 is now going to be 1 times S1. And now we can compute Z2 equals XW2 plus B2. How big is W2 going to be? That's going to be, well, we know it has S1 inputs, so it's going to be an S1 by S2 matrix. B2 is going to be a 1 by S2. And now we'll compute A2, A sub 2 equals G sub 2 times Z sub 2. So what is G1? Probably ReLU. G2? Probably ReLU. But you could have different intermediate activation functions. Often, you have the same one for every internal one, and then at the end, you have a special activation function. But we could have different activation functions at every layer. So what we've got then is, this is layer 1. This is layer 2. And we go for as many layers as we want, until finally, we're going to say Z sub L, the last layer, is equal to, we had a mistake here. I said Z sub 2 is equal X times W of 2. Of course, we are applying this matrix multiplication and addition to the output of the previous layer. So this is going to be A sub 1, W2 plus B2. And finally, when we get to Z sub L is going to be A L minus 1 times W L plus BL. And again, WL is going to be of size SL minus 1 times SL, and SL is the number of outputs, since this is our last layer, and B sub L is going to be 1 times S sub L. And then A sub L is G sub L applied to Z sub L. So every one of these within this one is the last layer, also called the output layer. And this one might often be called the input layer. And these are intermediate layers, or sometimes called hidden layers. Let's go ahead and rewrite this in a more general form. So every one of them looks the same, except the first one, because the first one, our input is x, and from here on we're doing a sub whatever that layer is, minus 1. Let's go ahead and redefine. So let's define a sub 0 equals x. And then what we can say is that z sub I equals a sub I minus 1 times w sub I plus b sub I, and that a sub I equals g sub I at z sub I. So we can kind of apply this L times, and that gives us our final result. Of course, we have a different wi, bi, we have a different gi. The output of one layer becomes the input of another layer, and so on. This is a neural network. And I think this is the easiest way to understand neural networks. Matrix multiplication with a matrix addition, application of activation function, rinse and repeat.